Good afternoon to everyone. I welcome all of you to the 68th lecture in the lecture series in nonlinear dynamics conducted by the Department of Nonlinear Dynamics, Bogoliubov-deGennes University with the support from PRUSA 2.0. It is my pleasure to introduce you today's speaker, Professor Arnaldo Gammal from Sao Paulo, Brazil. Professor Gammal obtained his PhD in physics from University of Sao Paulo, Brazil. After carrying out postdoctoral studies for a few years, he joined as a faculty member in the physics department, University of Sao Paulo, Brazil, in the year 2002. Since then, he is working in the physics department at various capacities. Currently, he is working as an associate professor. Professor Gammal's research interests cover Bose-Einstein, condensates, solitons, coherence in atomic medium, and matter waves. Professor Gammal has published a large number of papers in Bose-Einstein condensates, and he is a collaborator of our colleague and students of our department. Professor Gammal has supervised several students and acted as a mentor for some postdoctoral fellows as well. I met him when I was a postdoctoral fellow at the Institute of Theoretical Physics, Sao Paulo, Brazil, in the year 1998. At that time, he was also doing postdoc with another faculty there. Since we were doing at different areas, there were not much interactions, scientific interactions between us. Anyhow, I'm happy to hear his lecture today. With this short introduction, now I request Professor Gammal to deliver his lecture. Over to you, Professor Gammal.
Okay, thanks a lot for the presentation. It's a pleasure to be here to talk to you all. And I've seen some people that already visited us, like Murugan, also members of Bharati Dasan University also visited us, like Kishore has been a postdoc in our group and other visitors also. It's a pleasure to meet you again. So let us start. The seminar is in two topics. Let me just put it on play here. Okay, now you can see everything, although I cannot see you immediately, but if questions arise, I will be glad to answer you in the middle or in the end, but in loud voice. I cannot see the chat. If someone make a question in chat, I cannot see. But anyway, so let's start with these two topics. The first topic is the breakup of fast rotating condensates in asymmetric traps. And in the second part of the talk, I will say about stability of mixtures in a bubble trap. So this work was conducted with Leonardo Brito, that's still doing a PhD, still doing a PhD with us. Alex Andriati that already finished his PhD and now he's working in companies, and Lauro Tomil, my collaborator also in this work from IFT. So what can I tell about breakup of fast rotating condensates in asymmetric traps? First, I will talk about rotation in trapped gases in general. Then I will discuss shortly the Thomas-Fermi approximation in these quadratic quartic traps. Then we compare the Thomas-Fermi approximation with full numerics. And finally, we conclude this first part. So we can trace back about rotating condensates from the work from Jean Dalibard, that he performed a rotation of condensates and by first time produces vortices in these atomic gases, although there are vortices previously in liquid helium, but in gases, Jean Dalibard was the first one to rotate and produces these nice first vortices in quantum gases. This was about 2000. Just after the group of Wolfgang Ketterle, they were successful in rotating fastly and bigger condensates, and then he produces several vortices as he increased the rotation and the condensate. He could produce an Abrikosov grid here, as he demonstrated. It was a remarkable success and also a demonstration of superfluidity of the condensate, because if it's not superfluid, you do not form this kind of vortices in this arranged way. So then I skip on to 2016, when we got visiting of Kishore Kumar, that was a postdoc in our group, and this collaboration also with Bose-Fermi and Sri Raman. And Kishore brought us some codes. He was running dipolar condensates and exploring regimes of rotation of these condensates, but in particular case of the dipolar condensates. So in this case, depending on how much he rotates, or how fast was being rotated in the codes, we observed that there was breaking up the condensate. The condensate was split up in two parts. As you can see, from A going to B, we are increasing the velocity of rotation, and finally we got a breakup. Everything of this was numerical. We didn't have at that time analytics, and we cannot explain sharply with our analytics this breakup. But the idea was very nice, that it was a new phenomenon that was described, but we have no analytic, just numerical calculation. Well, passed some time, we were trying to understand this breakup. So we already knew that we have breakup on fast rotation. The question is, can it be observed in non-dipolar gas? The question is, if it can be observed in non-dipolar gas, it will be much more easier to perform in a lab, because very few labs are able to perform these experiments in dipolar gases. So a question may be if this phenomenon of breaking could be observed in a non-dipolar gas, so as much more labs could do that. There is a problem with fast rotation. If you just have an harmonic trap and you start to rotate it too fast, at some point you can overcome the harmonic oscillator trap, and everything goes out, and you lose the condensate. It's like rotating a ball with a string very, very fast. Once you rotate it too fast, the ball can overcome the force of the string, and the string breaks up and you lose the ball. Well, this is in a thinned experiment, but of course can be done with a very thin string. You can do that, of course, classically, let's say. But it happens also in quantum harmonic trap. Also, if you rotate too fast, you lose the condensate in a purely harmonic trap. Typically, to overcome this problem, you add up a quartic trap. So a trap with power of power of 4. With a quartic trap, you can maintain confinement and you can rotate as fast as you can, and you do not lose the trap. This was well described in these earlier papers by Fetter and also by Dalibar group. So harmonic plus quartic calculations was numerically done with by Aftalion and Danaila in 2004, and when they rotate this too fast with a quartic trap, what they observed is what they call a giant vortex. So what happens? When you rotate it too fast and faster going from left to right, what you have is that somehow all the blackness of this vortex go to the center, they gather together, and you have nothing in the middle, and you have this big vortex, let's say. Let's. Okay. To describe this problem, we start with the Gross-Pitaevsky equation, but here is already without time. We remove the time in the stationary form. We assume that the wave function is stationary, so it's psi to the multiplied by exponential minus mu, etc. And when you do, you have this stationary Schrödinger-like equation, but in fact, when you have this psi square, you call it the Gross-Pitaevsky equation. And also we have this potential, and this potential is a quartic trap, but you can switch the kind of quartic trap that you have. So this trap can be quartic in both directions, can be quartic in the x direction, and can be quartic in the y direction. We are considering here a two-dimensional problem. We assume that the third dimension can be swallowed up in some transformation. We are assuming that we have a pancake trap, so we don't have the third dimension. The z direction is already integrated. We assume we have Gaussian distribution in the z direction. In this configuration, we just have the condensate in two dimensions. And here we consider that either it have x quartic potential or x quartic plus y quartic potential. So sigma equals 0, x quartic, and sigma equal 1. You have r quartic. So it's just quartic potential added up. So let's describe first the case of x quartic confinement. And as I said, I'm just describing the non-dipolar case. So in the beginning, we did some numerical experiments with this. And in the numerical experiments, we found it useful to consider this a square x squared term. This a square is a negative harmonic trap, so it's negative. I will explain later that we can remove this negative part later, but from the beginning, adding a negative part, it will ease the breakup. So in the beginning, we are very concerned about the harmonic trap could not sustain, but now we are even doing it negative because we now have a quartic trap, this b square x4, and this quartic trap can overcome everything and can sustain the condensate. So we now added a small negative part to ease the breakup. It was useful in the first simulations. So if you make y equals 0, this is just a double L, okay? Is exactly, although it looks a little clumsy, this formula, it's exactly a double L. You can check. So from Thomas-Fermi approximation, it's a well-known approximation that if you have, for instance, a very big pancake condensate or something like that, the variation of the wave function, the second derivative of the wave function comes very slowly. So it's compared with the g square that measures the interactions of the condensate. It can be negligible. The nabla square, let's say the dispersion term can be neglected. And once you neglect the nabla square, you get this Thomas-Fermi approximation. And writing this first expression, you see that psi square equals to me over G. Me is, I call it here, me Thomas-Fermi, and just have this other term. And in particular, now you have, because of this term of omega LZ that we got prior, it transforms itself in this omega square R square. Details of this transformation you can find in Fetter. He has a justification for doing that in his review. So there is a justification there, but I will not go in all these details. You can just go to Fetter and see if you understand that, how he justified. In fact, it works. It works very well. So this term is transformed to omega square R square. What happens that the density must be greater or equal 0. You cannot assume negative densities. So once you assume this approximation, this expression psi square must be always positive, of course. And so you must keep this right time mu Thomas-Fermi over G. You must keep all this expression minus 1 over G. You must keep it at least positive or maximum 0. If it's at 0, the density defines the borders of the Thomas-Fermi approximation. And also, it must satisfy the normalization condition. So in this expression, and not, let's say, when you make in the center, then it will be n0 and 0 omega. You have it when you do it 0, equaling the right side. You will discover that at the break point, you must have. I mean, this is the center of the condensate. So the center of the condensate, if you are going to break up, of course, the density of the center must be 0. And if it is 0, the right side of this last expression must be 0. So you got an expression that mu Thomas-Fermi equals a to the power of 4 over 4b squared. So it must happen this. So you know how much is the mu Thomas-Fermi when there is the breakup. This contour that the density is 0 at the borders, you must solve it for being equal to 0. And before and after breakup, they are similar to Cassini ovals. So it's a well-known mathematical thing, these Cassini ovals. And they, if you just browse in the web or something like that, you will find these nice figures that very much resemble what we got first with dipolar condensate. So when you start to split, they in the middle they form this like Bernoulli lamniscate that have a similar of an 8, and finally you get the breakup. You can write it in polar coordinates. Polar coordinates were very friendly for describing this problem. So we understood that also the breakup can be identified with absence of real solutions of this angle describing in polar coordinates. When you have theta equals plus pi or minus pi, you have no solutions at this angle. Okay, there is no real solutions on this. You can define the radius minus and the radius plus from the when you trace a straight line here, you'll find 2 points. And the first point you can understand, well, it's quite hard to see. Maybe you can see here. So the first point is here, you define by R minus, and here you have R plus, okay? So this internal and external radius, they must, if you increase theta, they disappear, and then you don't get any more R minus and R plus. So of course you have broken up if you don't have this this solution. And at theta equals pi over 2, you don't have any more solutions. So here is the description in polar coordinates, and you have to do all these calculations in polar coordinates and make the density 0 at some critical x and y critical. And doing, it's a kind of algebra, and doing all this algebra, you got this, we got this expression that g p to the power of 4, it corresponds to integral, to this integral, and we got this fancy result that we must check against our numerics. In particular, this angle, this critical angle, is also given by this expression. So then we started to check if this formula is satisfied. If we got this condition for breakup, we got this expression. So we took, so we make this plot for a equal 0.5 and a equals 0. And we tested this for a equal 0.5, and we can see our tests. So these circles are our numerical tests using full Gross-Pitaevsky equation without going through the Thomas-Fermi approximation. So we solve numerically the Gross-Pitaevsky equation in 2 dimensions, and we can follow the results along these circles for one parameter of GB to the power of 4. This is 0.05, these circles, and the other, the triangles, is another parameter that I will show you. So going through these circles, well, it means going up, it means we are rotating fast and faster. So let me just go like here. So going up and up and up, we are going faster and faster. And let's see what happens. So here is the pictures. So just going. So we expect the going faster in these circles about, let's say, 0.4, something like 0.55. We must have this big breakup. And in fact, we confirmed that you can see in these black squares omega 0.3 in A, then we increase to omega 0.4, 0.5, we are almost at the breakup. Please note that these are numerical calculations. This color inside condensates are numerical, and the dashed white line is the Thomas-Fermi approximation, the Thomas-Fermi borders. So we can see a remarkable agreement between the Thomas-Fermi borders and the full numerical calculations. It was quite astonishing that it could predict so well. We were very well used that the Thomas-Fermi could predict the borders of a condensate, but it's not so obvious for us that it could also describe in this asymmetric case and describe everything in the breakup. So if we look at the right panels here, the right panels here, and these right panels, we can see the comparison of the Gross-Pitaevsky full numerics with the Thomas-Fermi, and we see that the majority of the profile is well described. And when we go to the right, this F plot, we see remarkably how good is the Thomas-Fermi approximation, even in this asymmetric case. So here I am considering exactly this case, and we can see that the Thomas-Fermi approximation can remarkably describe this, and also can predict the exact point, not exact, but in a very good approximation how or when it will break up. So here is for another parameter, is for triangles. Exactly, if we go back, we see that the triangles, the breakup is predicted to happen around 0.7. And exactly what happens in this parameter for G equal 2,500, we also have this remarkable breakup from 0.7 to 0.77. And it produces these amazing pictures that we have also this critical value of rotating very well described. And also it's interesting to see the phase, how the phase appears, showing exactly that there are many, many vortices. In our paper, we also described a discussion about the Feynman rule of this vortex, but I will not go into these details here. And then we also described the other case, that the R-quartic confinement. First, we described it that we have confinement. Sorry, we have quartic confinement just in the x direction, and now we describe also that you can another case that you have quartic confinement in both x and y direction. And in this case, also using Thomas-Fermi approximation, we have a critical velocity for appearing of the giant vortex, as I described it in the beginning, and also a critical velocity for breakup. So we have similar plots. Also, theory is very similar. We have G in the GB to the power of 4 as a function of omega, and also we have when we passes from different parameters here, going increasing the frequency. For instance, for GB to the power of 4 equal, let's show you, when you are here and you go through this region, depending on how you go, you pass through breakup and the giant vortex formulation. So this case is more involved. So it appears there are two curves, one describing the appearance of giant vortex, and then another curve describing the breakup. So this I can show you some pictures made in Thomas-Fermi. So there is this regime that there is breakup as before, and top there is Thomas-Fermi, and down there is Gross-Pitaevsky full numerics, and there's another time remarkable agreement in this case. And when we increase the G parameter, the interaction parameter, then we have a formation of a giant vortex. So first we form a giant vortex as we increase the omega, and then there is a different kind of breakup. It breakups in two half moons like this. So this phenomenon in the quartic R trap, the phenomenon is more involved. You form first the giant vortex, and then you have the breakup, as I said, when there is no more at theta equals pi over 2, you cannot have condensate. So this is a good condition for breakup. So two different kinds of traps, different kind of breakup. In the second one, the R to the power 4, you have a formation first of giant vortex, and then you have breakup. Here's a remarkable picture, enlarged picture that can happens to your condensate, depending on the kind of trap you build. So concluding this first part, breakup can be achieved in rotating non-dipolar quantum gases in asymmetric quadratic traps under X or R quartic confinement. So in both kinds of confinement, we can have breakup. Also, Thomas-Fermi is a remarkable approximation. It can be well applied in this asymmetric cases with great agreement, remarkable agreement. In Thomas-Fermi approximation, the solution for critical rotations can be found analytically for giant vortexes and for breakup. So this is the first work as we have. I don't know if you want to have all the questions at the end, or you have any questions about this first part. If you have any questions, I will be glad to reply. Yeah.
Yeah, there is a question. You want to take it now?
Yes, can be it now.
Yeah, Anirit, you can raise your question now.
Okay, that was a really nice talk, sir. I really enjoyed it. My question is, can you go back to the slide where you produce those giant vortices for large omega values?
Yeah.
Yeah, what I'm really yes, this one. What I'm really surprised here is that you are going beyond. You're going for such large omega values. My question is, why doesn't it go into a more turbulent state? Why can't we observe turbulence? Is it because of the quartic confinement?
Why? I didn't get the question. Slow down, please.
My question is, why isn't the condensate going into a more turbulent state?
Well, to go to turbulence, well, we don't have turbulence in this case. We didn't find any turbulence. You mean rotating fast? Well, even in the experiments by Ketterle, they rotated fast and they find Abrikosov rules, grids, is what we found too. We don't have this turbulent, we didn't find it. I don't know the details why we don't have turbulence. In principle, we should go to the Abrikosov grid. To get turbulence, you must rotate in a more fancy way, like a washing machine, as well Vanderlei Banhato used to talk to speak in his talks. He says you must have a washing machine, and we don't have exactly a washing machine. We are orderly, just going slowly and slowly, increasing velocity here. We don't have this washing machine. Okay.
Yeah. Thank you.
You are.
Okay, I have a question.
Yeah. Oh, yeah, please go ahead.
Yeah. This is regarding this G value of the interaction strength linearity. So you got, I think it's more than, is there any critical value at which Thomas-Fermi will work? I think that's the first question.
Yes, you must have the G sufficiently big for it to work. It must be big compared to. It must be, but of course, it is an approximation. But when you have the Grosspitaevsky to compare, we can manage this. Okay, let's compare with numerics if it's still working out. There are some criteria to match Thomas-Fermi approximation, the length scale, compare it to the harmonic trap scale or something like that. There are some criteria, but of course we always have numerics to, okay, it still works. Yes. And it's still working in this. Of course, if it's very, very small, or go to zero, if G equals 0, of course, it works very poorly because you are going from Gaussian to parabolic trap. So it's more or less soft transition from Gaussian to parabolic. So Thomas-Fermi will be poor for small G. But in these cases, we analyzed it was big enough to remarkably describe it. Okay.
Okay, thank you.
Oh, Professor Malimer, you can.
Yes. Hola, now. Nice to see you here.
Oh, glad to see you too.
Okay. A question. Did you consider effects of the elliptic deformation of your rotating trap on this pattern formation?
You mean, in principle, when you start to rotate fast, you mean that it will be more or less bigger, some profiles will be bigger at the like the solar system, or something like the Saturn wings, something that will be bigger in the borders, I believe you are talking about. But because as you rotate fast, it will be less dense in the center and bigger. Yes, there is a three-dimensional effect, but we have not considered this three-dimensional effect. We neglected. I think this was your question.
Well, this is also interesting, but actually the exact question was different. I'm wondering that if your two-dimensional trap is not exactly circular, but is elliptic, it has some eccentricity, then it will probably affect your symmetry breaking and other phenomena.
No, yes, there it's not. It is centered, but it's asymmetric in x and y.
Yes, yes.
If you see the expressions here, I have an A. In this A, this controls the asymmetry. You can make this. You can change this A to 0. To 0 is bad. Is from physical understanding is more. Let's say. It's more in the direction you say it's asymmetric. You see,
yes, yeah.
One here in front of y, and this is completely asymmetric. Yes, it is completely asymmetric. This is the idea. It must be asymmetric for breaking. If you make it completely symmetric in x, y, you have like you go back to Dainala and Aftalion paper of giant vortex. Then everything is symmetric, and you have. You must be a symmetry. There must be a symmetry in x and y to get this giant vortex, to get this breakup.
Okay.
Okay, so let's go to the. Of course, you can ask more questions about this at the end, but let's go to the continuing. So now let's consider. We now move on to a different problem. It's a problem about a bubble trap or shell trap. You can call whatever the way you want to call it. That people recently has been interested in other geometry. In fact, people have been interested in this geometry for a long time. I've shown you, but now it thinks that people can do this experimentally. So let's to discuss this condensate mixture and the bubble trap. Let's start with motivation, main equations, stability analysis, and time-dependent evolution, and finally conclusions. So the motivation for this is the exploration of BC in different geometries. This is a long-standing possibility, is the shell geometry that has been realized on bubble trap or shell trap, whatever. Bubble trap is inaccessible on Earth due to gravity. So when you apply gravity, you hardly can you cannot apply it, just not turn on in the lab. It's inherent in the Earth-based lab. You have to have gravity. You cannot turn it off. What they devised is to do this experiment on the International Space Station in microgravity environment on a space station, and this was NASA Atom Code Laboratory. So this is a description of the possibility of shell traps or bubble traps. Was you can trace back from Zobai and Garaway 2001, then 2004, and now things came back with a description of experiments in 2019, sorry. So because of this possibility in space station, several works on bubbles appeared recently. The area that was dormant recently wake up, And we have these several papers by Italian guys like Salashnis, Prestipino, Tononi. In 2009, you have in São Carlos, you have Banhato groups with Monica, Madeira, and Beretta. We have also Hen group in São Carlos with his group. Also, we have Padavich and this group in 2020, and Smita Visheshwara, I think she's in the US. And also, and then finally, these experiments that started in 2020, first observation of BC 2020, and now observation finally in these atomic bubbles in orbital microgravity. And also experiments by a group of Hélène Perrin recently appeared, trying, in fact, they made a beginning of a bubble also, but this is on Earth. The last paper I added here, it's made on Earth, but cannot make exactly bubbles. Always this problem of gravity still remains, but at least they made part of the bubble. Anyway, so this gave us some motivation. We have worked previously. In fact, I have a paper with Boris with Boris Malomed about mixtures and studying stability of these mixtures long time ago, but not in the bubble geometry, but in a condensate. We have rotating mixtures, and what we saw is the possibility to work on mixtures also in this bubble shell. And we were inspired also by Malomed work in that is this miscible and immiscible states in binary condensates in ring geometry, so a new journal of physics. And this is description of the ring geometry, and inspired by this this work, we asked, well, how it will change in a bubble geometry, the generalization of this ring problem, how it will be in a bubble case. So, so we have to model this this same problem. So this is fairly the same equations as described in the ring problem. We must take care with now a lot of care with the boundary conditions, since it's periodic everywhere in the sphere. Once in the ring is periodic boundary conditions, but here is periodic everywhere. So we have to deal with all these problems. At least numerically, we have to rewrite our codes. So we have to rewrite our codes in this angular coordinates. It was the solution we got to solve this. Some people like Adhikari have solved this problem three-dimensionally. They solved it three-dimensionally, but it was much more complicated for what we wanted to do. So we decided to just describe what happens in a thin shell. So this is a reduction to 2 dimensions. Also in a thin, you consider that you have a very thin shell and you have a reduction, and you have only, let's say, a 2-dimensional effective problem with theta and phi coordinates. So you just only have, we remove it. Of course, we have the equations in 3 dimensions, but we consider that we have a very thin, something like a Gaussian distribution in the surface of the shell, and then you remove this dimension, and you are effectively in 2 dimensions on this thin shell, and then we built our codes considering that we are in 2 dimensions. So you just have only this theta and phi coordinates. So here is removed the r the R dependence. So removing R dependence, you just have this nabla square in terms of theta and phi, and you have this effective rescaled interaction that you divide by R. This gamma j chi, it's an effective interaction already. Removed this dimension, so gamma j chi is a dimensionless parameter. So you have everything in length units of R, energy units described by h squared over m r squared, and you must have this skin for doing this approximation. We obtained that the skin delta, the skin is the length of the shell, much lower than 8 pi cubed over gamma jk. So once posed our equations, we first looked at solutions of azimuthal symmetry. In principle, is the same thing as already done by Padavich, but not for mixtures. So Padavich studied Padavich and collaborators studied these mixtures, these solutions, but we are trying to consider mixture. But let's say homogeneous solutions have this form, should have this, not exactly homogeneous, but considering if you have spin 0, Sj 0, you have homogeneous solutions, but if you have spin plus or minus 1 or plus angular momentum plus minus 1, plus minus 2, you can consider that you have vortices in the North Pole and in the South Pole with this condition. If you have S equal 1, you are considering that you will have a phase rotation and you have a vortex in the North Pole and the counter-rotating vortex in the South Pole. So we just assumed this initial stationary solutions, and from these stationary solutions we can draw linear perturbation theory to find somehow the Bogoliubov modes to study the stability. So we build our system with one condensate have this function, the other condensate also having the same function. We start from homogeneous between condensates. There is no mixtures between them. They are with the same initial wave function. And we study how this evolve, it breaks up or not, or if it not breakups, if mixes or not, and what will happen. So this is a standard Bogoliubov-deGennes equations, but as I said, you have to translate former works that we have in XY direction, with just in XY, you have to translate to the sphere. And we were successful in doing that. We solved the model equations. We got the Bogoliubov-deGennes equations in the same way as we did previously. I did with Boris in former work, this matrix, the Bogoliubov-deGennes matrix for mixtures, must be diagonalized numerically. So we first found the ground state of the system, then we plug this ground state in this matrix, and then we diagonalize numerically this matrix and obtain the eigenvalues. So these eigenvalues are valuable for studying stability. Once you have imaginary eigenvalues, it means imaginary frequencies, and of course, imaginary frequencies lead to instability of your condensate. Okay. So for S1 and S2 equals 0, if you have from one species, you don't have vortices, in the second species also you don't have vortices, Bogoliubov-deGennes is simple and can be computed analytically through spherical harmonics. So in this case, we can exactly match previous calculations from Boris in 2009, from Boris Malomed 2019, and we have very, very similar expression, although there is difference because you have L square here, the angular momentum, but the expression is very similar, and in the same way we understand that we can somehow have some increase of stability when you have confined geometry. So as in the ring, they obtained that you can have further stability. We also have further stability as should be in the spherical, but slightly different in the spherical bubble. So here I show the eigenvalues for these different modes, for modes in spherical harmonic modes. So we have L equal 1, 2, 3, 4. So then we have imaginary part. Let me just skip for here. We have imaginary part here. So you start with 0, and then once imaginary part starts to grow, you have unstable. So at this point, things start to be unstable by this mode, and then this mode gets unstable, and so on. So this is, you can play analytically, and you can find in the right side, you can find that instability grows up as you gamma 1, 2 equal 10. You have everything is stable. When you increase this gamma 1, 2 to 20, things get completely unstable, and they mix. You lose miscibility of the condensates on the skin of the shell. Then we studied a similar case we did long ago with Boris. So we have the case of hidden vorticity. We only analyzed these two cases because if we start to study all the cases, the work is too big, it's too many things to analyze. So we just analyzed the case S1 equal S2 equals 0, and also the case of hidden vorticity. The hidden vorticity, you have one condensate rotating right and the other condensate counter-rotating. And you have, in one condensate, you have vortices in the pole, and the other anti-vortices in the pole. They're exactly counter-rotating, and then the diagram cannot be solved analytically. You have to solve for the wave function numerically, as did Padavich for one species. We also solved it numerically. And now, considering the two species, symmetric two species, we start on them two symmetrically, but one rotating in one direction and the other in the other direction. Then here is the analysis of these eigenvalues in the left panel, considering both interactions, self-interactions equal 10, and we change the interactions gamma 1, 2, but that is interaction between species, and see that there is a whole diagram of eigenvalues. So whenever you have imaginary eigenvalues, you have instability, and here we are plotting the maximum imaginary eigenvalues for different instability modes. And in the same way, we also made these plots for gamma 1, 2 equals 0, and now changing the other parameters, gamma 1, 1 and gamma 2, 2. And also we have this plot, and changing all these parameters, it's possible to build a stability diagram for this case. So since this case is much more complex Then the case of 0, when prior we could solve analytically the case of S1 equal S2 equals 0, it was very easy, but now it's much more complex. For S1 equal minus S2 equal 1 is more complicated. And here I show you the whole stability diagram. So in this very dark blue, everything is stable. I mean, you have big gamma 1, and big gamma 2. Let me just describe it here. So here in this region is everything stable. So if you put gamma 1, gamma 2, something like 30, you are exactly here in this gamma 1, 2. So depending on the gammas you have, and here I also will show you this case of this star. I will show you this star, and the other, say, and this case here also, this point I will show you in a couple of minutes. So here is the case gamma 1, gamma 2 equal 10. Let's say it is the case, let's say it's the star case. Gamma 1, 2 equal 8 is stable, and gamma 12 is unstable. So this is the case we are analyzing here. This is the X case. So depending on the gamma 1, 2, you go from stable to unstable, going in this direction. So we checked our stability diagram for several points, and one that I just wanted to show is the X one. Let's go there. So here gamma 1, gamma 2 equal 10, and then as I said, when you go from gamma equal 8, you are stable. So you can see this dashed red line here in the left panel is gamma 1, 2 is 8. So it's always stable as when you run a Gross-Pitaevsky equation. And once you go to gamma 1, 2 equal 12, it's completely unstable. And it's stable, and it oscillates and starts to make these oscillations. So in the right panel, I show you these oscillations for gamma 1, 2 equal 12. So it starts, angular momentum is exchanged continuously between the condensates. And you can define the miscibility parameter as defined here as lambda t. You have this miscibility parameter, and you have these oscillations. So miscibility parameter also, as you see, this lambda psi 1 and psi 2, it starts to oscillate continuously. So it's a breathing mode, you start to continuously oscillate. So this is in this region that's unstable, but periodically oscillate. And here I also considering the star mode, the white star mode. Now we have gamma 1 equal gamma 2 equal 10, and gamma 1, 2, the interaction between species is negative. So in this case, it's just to show you, because the diagram is very complex, we have checked several points, but for demonstration, we choose some points to show you how it happens. So in this case, we are showing two views. In here, how instability mode grows up. As I show, if you go to the diagram, you see that this diagram have unstable mode, like m equal 3, something like m equal 4. Let's see. And here is the m equal 5. Gamma 1, 2 is 95. Gamma 1, 2 is 95. Sorry, it's positive. It's positive. Gamma 1, 2 is very, very big. positive 95. Sorry, I think it should be minus 95. Yes, there is a misprint here. I think it should be minus 95, if I remember. Anyway, let's see. We can see the instability, and t equals 0. It starts to get unstable. In t equal 3.85, it develops this mode, and then t equal 0.15. As you see, it breaks up in the 4 parts. So the instability mode equal 4. You split it in 4 parts. And here we are showing species 1 at the left side in 2 views. In the viewing from the equator or viewing from the North Pole, depending on where you are viewing. So here, let's see. So here you are seeing from the equator, and here you are looking from the North Pole, as here is indicated. So you have species 1 and species 2 to see that. And here I can show you, here, now is the star, sorry. Now is the star, and the star, here, the star, the white star here, we will show you how instability develops. And we have, sorry, we have a small movie. I don't know if I can. I will play it here, but I cannot play it. Now we can play it. So you can see as time evolving, you start in this way. And this is in the S1 equal 1, S1, S2. This is the hidden vorticity case. And as time evolves, finally, instability develops, and it breaks in 3 parts as the mode predicted. So it will break exactly in 3 parts. So it collapses. In fact, what happens, it collapses in 3 parts. It starts to shrink, but it shrinks in 3 different parts of the condensate, of the sphere. So there is maybe I play another time because it was too fast. Now you can see it, how it develops. It was a very nice movie that students prepared. And here's the phase also being shown, but the density is here clearly, and there is a quite delay. And finally it happens. So this everything, this time-dependent calculations confirmed our Bogoliubov analysis, and one reinforces the other. Either Bogoliubov analysis reinforced our numerical calculations, or numerical also reinforced Bogoliubov analysis. There is another work that appeared recently. It's they have a different analysis. They consider also different masses, mixtures. We consider the same species, but in different hyperfin states. We are not considering different masses because it will be more complicated analysis. We have an extra. We already have too many parameters. Gamma 1, gamma 2. If we put masses, it will be more complicated. So in our first approach, we consider the same masses, but the different species come up from being in different hyperfine states of the same atom. But they considered also mixtures of different masses. But it's different. It's not. They do not analyze these instabilities as the same way as we did. So to conclude this part of the mixtures in the bubble shell, we can say that homogeneous mixtures in bubble can turn to be unstable depending on inter and intra-species, that means gamma 1,1, gamma 2,2, depends on this interaction. In bubble confined geometry, the critical point G12 is also extended as in a ring, as shown previously by Malomed and collaborators. And unstable modes can be analyzed by Bogoliubov-deGennes, and timed evolution confirmed our results. Okay, so this way I finish this presentation. Just my friend that likes quantum fluids. Thank you.
Thank you, Professor. So, forum is open for questions, clarifications, doubts.
Okay.
Yes, Professor Molive.
Yeah, thank you. So now you showed a movie in which the onset of the instability started with a rotation, and then it became unstable. What determines the sign of the rotation? Clockwise or counterclockwise? How do you select the particular direction of the rotation?
Well, in the hidden vorticity, one is rotating in one direction and the other is rotating in the other direction. They are counter-rotating. So if you exchange them, it will be the same. It's just a symmetry.
So you showed only one component, you mean?
No, two components. I showed two components. Sorry. I showed in this movie. I showed one component because because
the other component rotates in the opposite direction.
The other component rotates in the opposite direction. So yes, the phase I am showing is just from one component. The density is the same for both because they are the same. But the phase I'm showing just for one component. If you want to see the two component evolution, you can see more detailed here. In this plot, we have the two components evolution. And then you see that one component occupies one space and the other component occupy in this mode. You see that they occupy different places. So I'm sure you are right. I'm showing just one component. The other component is not shown in this.
Okay.
Yeah, it will be more interesting to show the both components. Unfortunately, we did only one component. Then we can see the evolution if the spots go together all the same or they not. But this is not shown here. But if I remember, I think they go all together to the same spot because it's attractive interaction. And the other one here is repulsive interaction. They go to different, they do not superimpose the modes. They do not superimpose here and here. They found different spaces to be allocated. But thanks for the question.
Okay. If possible, another short question. In some cases, when your instability is strong, can you observe transition to a turbulent state?
Yes. We can. It's very turbulent. But I don't have, I'm not sure I have any picture of this. Let me see. No, I don't have this in here, but I have in our paper. Let me just recover it. One moment. In a second. So I also have this. Let me change sharing. One moment. So, can you see this? It's going. You see? Yes, there is some some chaotic behavior
Okay. Okay.
when you put s equal 1, s equal -1 and 10 and 295. There is this chaotic behavior, like
Okay.
chaotic in the world. The world becomes chaotic now.
Okay.
I think this is what you wanted to see.
Yeah. Okay. Muito obrigado.
You're welcome. Okay.
Yeah, it's nice.
So, Anand, do you have some questions?
You mean me? No. It's
Yeah,
okay. Thank you. That's fine. It's interesting. Very interesting.
So, are there more questions, clarifications, Anirudh?
No more questions, sir. It was very interesting. Thank you so much.
Okay, very good. Well, I see there's. You can watch it in the auditorium. I have seen the students and
Yeah, the graduate students are
very nice. It's very, very nice. Unfortunately, it will be a good opportunity to visit you, but at this moment it's not so easy to go to India. Anyway, whenever I have an opportunity, I will visit you in Tamil.
Sure. Yeah, now you can travel.
Yeah, because many of you already came to visit us, so maybe opportunity I shall also visit you.
Yeah, that's right. Yeah.
Long collaboration with your university. And also I have collaboration with Rada. I was seeing the map, it's like 2 hours from you.
Yes.
You know Rada. Yeah, also in Tamil.
Radha. She's talking about Radha.
Rada. Okay.
3 hours journey. Yeah.
3 hours.
Yeah.
No, in Google Maps it's shorter.
Okay.
So, are there more questions or clarifications, students?
Okay, if you have any further questions, you can also ask me by email. I'll be glad to collaborate. You already collaborated with some of you, and we are always open for. If you have an idea, okay, I want to run bubbles in different shape, we can discuss that. We already have some codes built. If you are interested, we are working on that. Okay, we are open
Maybe
to.
some of them will write to you.
Okay.
Sure.
So, since there are no more questions, I would like to conclude the session by thanking Professor Arnaldo Gammal for accepting our invitation and giving a very interesting talk on Bose-Einstein condensates. Thank you. Thank you, Professor.
Thanks for the
Thank you,
invitation.
Thank you, Arnaldo. Thank you.
Thanks a lot for your attention.
Thank you.
Okay, thank you.
Thank you. Bye.
Bye-bye.
Bye. Ciao.
Ciao.